Yep, that works. Let's get you in a better spot. All right. Let me pull up. Well, I don't know if I want music today because I'm going to be reading and I'm going to be thinking out loud a bit. I'm going to do my best not to sneeze into the mic, but I've been congested. You can probably tell. I think I've been getting hit with allergies or something because I'm congested and I'm sneezing hard regularly. So hopefully I will know when that's coming and be able to decrease the impact. Also, let me make sure I've got, sometimes I put my mic too low and I can't reach my keyboard. Sometimes it feels like it's too high and I can't see my screen. That'll have to do. Hopefully that's good. Hopefully that's good. So I am back to my SAT solvers project, and I haven't done this for a couple of weeks. Last time I worked on it, I read the CDCL SAT solver that I found on GitHub, and I've actually gone and implemented one now. So let me show you that because it's kind of fun. Let's see, I think I put that under jams. Yeah, so I made this little project called FatSat, and it's not particularly carefully optimized yet or anything like that. It's just the basic implementation of CDCL that I read last time, but in my own style. So it's all based on arenas, and it's in one file mostly. And I got a little file here testing it. So that was cool. CDCL is cool, and I think I got a good handle on that. Now, I don't know what MiniSat is going to bring to the table, but the other thing I did last time was I got MiniSat here to compile. So this was compiling. Let me double check. I don't know why it's saying that, but this is the whole thing compiling. So we can build MiniSat. Now, I'd like to walk through it because if I can build the code, then the next thing I can do is I can actually use a debugger to read it rather than the text editor, which I think would be a little bit more interesting in some ways. So I want to give that a shot. Let's see if I can set up a remedy instance that will run that executable. So it's right here. MiniSat build. All right, MiniSat simp and MiniSat core. Where are those coming from? Let me look at the build script for this real quick. MiniSat core is from core/main.cc. MiniSat simplest. Okay, let me read what those are about real quick. So I don't think any of this. Yeah, let me make sure I have all the code open. I haven't set up a 4-coder project here inside the MiniSat folder or the SAT folder or the research folder. So I don't have any project organization around any of this stuff yet. I'm just kind of navigating files loosely, which makes it a little bit more difficult to find things sometimes. So now I should be able to do, yeah, let's look at what main core says. This is just copyright stuff. I love it how people always need to start their software with a copyright notice, but then it doesn't actually say what the file's purpose is. So like, I don't know how you're supposed to figure out what a file is quickly. I don't know what people's plan is, but it usually isn't at the top of the file. Maybe there's a README. Maybe that's what they're expecting. A core version of the solver, an extended solver with simplification capabilities. Okay, cool. So core is the basic one, and simp is the complicated one because it includes simplification capabilities. So that's probably some of the stuff that's most interesting to me. Like if we look at core and it turns out to be another CDCL solver, not a lot to see there. So some other things to look out for while we're going into this. This is a C++ code base, not a C code base. We are going to be seeing templates. I think we're going to be seeing classes. So if you haven't seen that for a while, or if you're not familiar with the C++ language features, we're going to be working our way through those. Luckily, I used to do enough of that I think I can handle it. But the debugger is also going to be pretty important because it's going to actually show us how the code runs, which with templates can be very hard to figure out without the debugger. So let's start with core, even though it's probably not the more interesting one, because, we're just getting started. We'll walk before we run. Let me see if there's any sign here of how to execute this. Usage, options, input file, result, output file. Our input may be either in plain or gzipped Dimax. Okay, I better figure out what Dimax means. So the first thing that comes up when I search Dimax is like a research lab, it looks like. Or is it I'm guessing it's a text format. Okay, I think this is more like it. Using the Dimax CNF file format. Okay, I think that's what we want. Here is the CNF file that corresponds to the simple formula discussed above. C simple v3 c2 CNF C p CNF 3 2 1 negative 3 0 2 3. Okay, what is this? What are we talking about? An example of a Boolean expression in 3 variables and 2 clauses. So we have our first clause is x1 or not x3. Our second clause is x2 or x3 or not x1. The file may begin with comment lines. The first character of each comment line must be a lowercase letter c. Okay, so these are one of those really bad file formats. It sounds like, just from what I'm seeing here. The kind of stuff that like people used to do to like organize Lexer generators and other. It's designed to be relatively easy to parse, and rather inhumane. It's not meant to be inhumane, but it's like it sacrifices all humanity. Right? There's nothing about this that is meant to be graspable or intuitive. It is meant to be trivial to parse in the C program. Comment lines typically occur in one section at the beginning of the file, but are allowed to appear throughout the file. The comment lines are followed by the problem line. This begins with a lowercase p followed by a space, followed by the problem type, which for CNF files is CNF, followed by the number of variables followed. God damn. That's such a bad... Okay. This begins with a lowercase p, followed by a space, followed by the problem type, which for CNF files is CNF, followed by the number of variables, followed by the number of clauses. Okay. What is it saying? Spit a p, and then the problem type, and then the number of variables, and the number of clauses. P, problem type, number of variables, number of clauses. Okay. The remainder of the file contains lines defining clauses one by one. A clause is defined by listing the index of each positive literal and the negative index of each negative literal. Indices are one-based, and for obvious reasons, the zero index is not allowed. So the obvious reason is that there's no negative zero that is distinct from zero in a signed integer. The definition of a clause may extend beyond a single line of text. May extend beyond a single line of text. The definition of a clause is terminated by a final value of 0. Okay, so a clause is a list of these indexes. It's terminated with a 0, so it doesn't have to stick on a single line. The file terminates after the clause is defined. After the last clause is defined. Right, so at the end of the file terminates. Okay. Some odd facts include the definition of the next clause normally begins on a new line, but may follow on the same line, the 0 that marks the end of the previous clause. Yet in some examples of CNF files, the definition of the last clause is not terminated by a final 0. Sure. Right. Okay. Yep. Got it. So that's good. What I want to see is if why don't we try to run our core program here, and I'm gonna write a CNF file for it. Actually, it looks like they might have example CNFs here. 100 variables and 660 clauses. Let's take a look. Not satisfiable. Okay. Thank you. Call this test1.cnf. For coder copy paste bug has to get in the way once. And there we go. So let's try to run that from here first. MiniSat. Build MiniSat core. Okay, if I run it with no arguments, it tries to interpret the input from the standard in stream, which isn't super helpful actually. Right. Okay. So input file, result, output file. Right. I remember reading that now. Okay. Input file is going to be test1 CNF. And we'll call this out1. I don't know what kind, .txt, I don't know. Yeah, okay. So that runs and it says on SAT. So that's cool. Let's start by reading what this output says. Maybe we can learn a little bit about what this program's internal structure is just from understanding what it finally outputs. And then I'm going to step through that same thing I just did again, but through the debugger carefully and see what we learn. Parse time 0 seconds, conflicts, original vars, clauses, literals learned, limit clauses, progress. I don't know what any of that's probably stuff that was changing while it was running, but it was too fast to see any of it. Restarts 1, conflicts 24, CPU time 0.004 seconds. So this file we just gave it took 0.004 seconds according to this timer. However, that timer is implemented, which is 4 milliseconds. So, you know, it might not be something you'd want to do in your game loop every frame, but you could do it. You could do it from time to time. You could get this job done, like, you know, during world generation or in a background thread if you needed to be doing it pretty regularly or something. So that's fast. It's still only 100 variables, but I'm getting a good feel of how fast it is, which is, you know, nice. Let's take a look at Remedy now. So we're going to be using the MiniSat core, and I want to tell it the same thing I just did on the command line. Test1.cnf. Where's Remedy? There it is. Test1.cnf out1. All right. Okay, first thing I'm noticing now that I'm actually stepping through it is that this is all on a try block. I don't know how exceptions will play into this, but we'll find out. Okay, not relevant to us. I don't know what floats. I don't know how floats will play into this, so that'll be curious to see. Or I'll be curious to see that. Okay, right, so we're looking at C++, right? So C++ hats on. If you see a function call that is also a variable declaration, that's a constructor now. Verb, main verb, verbosity level. So verb's a abbreviation for verbosity. 0 is silent, 1 is some, 2 is more. 1, I'm going to guess that's our default. And we set the range from 0 to 2. So this is command line parsing stuff, right? This is telling it how it wants to grab these parameters. So verb is going to be the default 1 with this range. Limit on CPU time, limit on memory usage. And then, yeah, it gives it the options. Parse options. Why don't we take a look? So I'm guessing these are just trivial constructors. Yeah. Okay. Let's keep stepping in. Okay. Okay, a lot of short variable names all of a sudden. So this is the name of the variable, the description of the variable, the default value, the range on the value. Then it creates an option, which is this thing, which does get option list, which is so it's a global list of options, option pointers, and it's going to get that list of options and push this particular option onto it. Yeah. We don't need to go into. We don't need to see this. We don't need to see this for now. Okay. Oh boy. Yeah. So that is a bunch of constructors which have also directly modified a global list of options. So when we go to parse the options now, yeah, you can see this is going in and getting that global list of options again. And it is scanning for each option in the list and for each argument. If we have a match, it's going to figure that out. There are none because I didn't pass any, so we should be able to get through to there. Parsed okay is true, actually. Oh, that's if not parsed okay. Great, so if I'm here, right, there we go. We never found any matches between the argument we were looking at and the, wait, what is that? Man, this is rough. Well, I can't really read this code effectively, but I can intuit what this must be doing at the highest level, which is it is using these options and the global list of options that are hidden inside the local variable inside the static function inside this class to prepare the parameters for the program from the arguments list, right? Just parsing command line stuff. Okay, there we just constructed a solver. I'm going to run again and skip to that part. Anything interesting here? So the solver has a lot of stuff in it. Look at this. This is the beginning of the constructor for the solver. This is the initialization list on the constructor. So in C++ land, when you're making a constructor, sometimes instead of setting variables by setting them, you set variables using this thing because it's fun and it's arcane and it's what you got to deal with. So opt var decay, where is that coming from? How are you seeing opt var decay? Double option. There's a bunch of static options up here. Interestingly enough. Okay, so I have a question. I know I'm getting hung up just on the options parser here. Extra options. These are the ones that are constructed locally here for this particular thing. If I go in here, and I go in here, and I go in there, and I go and put a breakpoint right there, and I run again. Yeah, look at this. Do you see what's happening here? We are getting code that runs before main. Here is just the runtime that actually makes that possible. Here we are looking at the line that does the constructor call for the global variable. And here we are actually looking at inside the constructor of that double option, and that's going to get added to the list. So before main ever runs, this global variable is filled with all of these. And then once main starts, a few more. I don't know why. But that's what it is. So whatever. Let's get back to the part that I actually want to learn about. So the solver has a bunch of these options here: verbosity, variable declaration, or variable decay. A lot of these look like they're going to get constructed right from the, or yeah, they're going to be initialized right from the options. So presumably these options probably have a way to cast themselves down to the type of the option. So like this casts down to a double, that casts down to an int, that casts down to a bool, that kind of thing. Yep, so there it is. You can see I just do a couple of step-ins and I find my way to this operator that takes the double option and casts it to a double. So the double option behaves as a double and also does this other stuff, modifying the list. Object-oriented programming is wild, folks. Okay, let's skip ahead to here and clock. I don't know what that is. Is that like the... C standard library clock? I forgot this existed. I always just think of like timing stuff. You have to go to the operating system because that's the only way to get a good timer. Am I right? Or was I wrong? Was the C standard clock always good? Consumed by the program, the value returned is expressed in clock ticks, which are units of time of a constant but system-specific length. Clocks per second, clock ticks per second. Okay, so I don't know how precise that clock is. It might be pretty precise. The way they're using it is a little bit not the best. It's no big deal. It's a nitpick. But it'd be a little better to not do the divide until after you have two different clocks. It's fine. So we get some random number here called our initial time. And we're thinking of these times as being in seconds because they've already been converted. So verbosity, which couldn't be one of the static variables, has to be set manually in the solver. Here locally, because that's where the verbosity variable exists. We then set solver, the variable, to the address of S. Presumably, oh my gosh, this is like classic C++ code. It's a doozy. Okay. So now that we've constructed the variable locally, we're going to this is probably a global somewhere. I don't know. I don't have a way to get to the definition of it from here, but we can do, if the name of the type is solver and the name of the variable is solver, and it's probably a pointer. Do we have a solver pointer anywhere? No? All right, so just give me solver then. I'm sure there's plenty of those. Oh yeah, they probably use, let me try this solver pointer. There we go. Yeah, the star's on this side of the space between, yeah. Okay, so this is a global pointer to a solver, which points to this local solver. That's not good. So the reason that's fine for this is that this is main. They probably want to be able to get the solver into other functions without any hassle. And so this is their way of passing it around without having to manually pass it around, which is fine, which just means like make the solver global, but presumably like they wanted to get the constructor underneath this constructor, and then C++ makes you do all kinds of weird stuff. So you end up with a local variable on your stack and a global pointer to it, which you just don't want to be doing. But oh well, here we are. Use signal handlers that forcibly quit until the solver will be able to respond to interrupts. We're in Windows, so I don't know exactly what this means. Hey, Chandu16 asks, SAT, what is that? Okay, great question. This code I'm looking at is a dead end anyway, so let me just step out of this. There's nothing interesting there. Well, let me tell you about SAT real quick. So, do you know what a Boolean variable is, right? If I have a Boolean variable, call it X, it can be true or it can be false, right? If I have a couple of Boolean variables, let's call them x1 and x2 and x3 and x4, then you can start to do things like x1 and not x2 or not x3, right? You can build these expressions out of logical combinations of Boolean variables, and these are you may call these logical expressions or Boolean expressions. So we have Boolean variables with logical negation, logical and logical or, to combine them. So this would be true, for instance, if x1 would have to be true for this one, and then either x2 or x3 or possibly both would have to be false. Right, so they couldn't both be true, but this one would have to be true, and then the whole thing would be true. So that is a Boolean formula. These we'll call our variables. Now, SAT is a tricky problem. SAT is the name for a tricky problem. It's the technical computer sciencey lingo name for a tricky problem, where I hand you a formula, and I ask, is it possible to make this formula come out true? So, in other words, is it possible to satisfy the constraints of the formula? So, for instance, if I gave you x1 and not x1, then that one's pretty easy. The answer is no. There's no way to make that true. You can make x1 true, and then you have true and, well, let's see, the not of x1 would be false, right? So true and false, and that's false. But if I make x1 false, same problem, right? So now I have, if I make this false, this would become true, but then this part would be false, right? So the problem of SAT, it's not to create Boolean variables, right? It's not to evaluate these. That's just evaluating Boolean expressions. The SAT problem is this formula possible to satisfy? And so it does not know certain values, and its job is to either say, yes, here it's possible to satisfy, and here's a way to set all the variables so that it works, or to say, no, that's not possible to satisfy. So that's the SAT problem. And a SAT solver is a program that solves that problem. Hope that makes sense. Hello, Babel. Welcome. Okay. So I don't know what the signal function is doing since we're on Windows. I'm ignoring that. It's a wild ride. We're trying to get to the SAT part. Chandu16 asks, again, what algorithms do you use to solve this problem? So you can do brute force. Brute force just means you look at all of the variables and you say, let's make them all false. Does that work? And then one at a time, you iterate through, okay, make the first one true, make the second one true, make the first two true, make the third one true, make the first and the third one, right? You just are kind of you're treating it as a bunch of bits and you're counting an integer up, seeing if any of the combinations work. So that's one fallback, but that's slow. If I give you 100 variables, then you have to count from 0 to 2 to the 100 to try every possibility. And if there's only a few options that work, you might have to go pretty deep into that to find it. So then SAT solvers try to find faster ways to do it. Last time I streamed, I read some code for an algorithm called CDCL, which stands for conflict-driven clause learning. So the idea there is, as you're going, if you find, I'm skipping a couple of steps here, but we're working on a simplified form. So it's not any expression, but it's a CNF. There's a lot of jargon here. The CNF means that instead of arbitrary expressions, we simplify it down to just ands of ors. So if we have a bunch of ands, right, like this, and then inside of those parentheses, we can have some ors. So we can be like x1 and not x2 or not x3, I mean, right? We can be like that. And we can be like, okay, this will be, let's say this one's going to be x3, and it's going to have an or x4, or not x5, and so on and so on. So we can have ands, we can have ors, but they have to be in this pattern. It turns out that any Boolean formula can be converted into this form by adding some extra variables. I'm skipping over how that is possible. I haven't actually implemented it myself before, so that's something I might learn about today or along the way on this project. But with the CDCL we learned last time, the idea was each of these is called a clause. If any of them, it turns out completely false, so all the variables in it have been set and none of them make the clause satisfied, then that clause needs to be we need to work on the set of decisions that led to that particular clause not working out, and we learn a new clause that sort of contains within it an idea that directs our future decisions and our future guesses. And then there's some heuristics spots where you plug in heuristics for how do you make your next guess to go as fast as possible. So that's one algorithm, and that's the only algorithm I know so far, besides brute force. So we're learning. All right, so setting resource limits, not relevant. Args equals reading from standard input. No, we don't need that. GZ file in. Argc equals 1. No. Yes. GZ open argv rb n equals null. Okay, so GZ open must be the thing that is loading in the file, right? So this is like an f open. In C, you have f open to open a file handle. It must be that because this had a dependency on gzip. So it must be that this is the gzip equivalent and is capable of decompressing the file if it's a compressed file. But it's going to just give us a regular file handle kind of interface, maybe. That's my guess. Hey, Brett. Chandu 16, I have not played around with distributed systems much. I've done some multi-threaded programming, so that's kind of similar. I've done a little bit of I've done like a remote computing thing where you had one computer that you were how do I want to describe this? You had one computer that was doing the interesting stuff that you wanted to interact with, but you had a separate computer that you were actually sitting at, and so you needed to set up remote connections to control the other one. So I've programmed stuff like that. None of it's ever actually been super good. I haven't gone super deep into that topic. I've also set up a website with some stuff, but I did that completely non-distributed. The only way in which my website does any distributed computing is that it sits on a cloud server, like a droplet kind of thing. So I'm sure there's some virtualization and distribution stuff happening behind my back there, but from my perspective, there's none. Anyway. Brett, so I'm kind of doing a learning jam project. The thing is, the learning jam technically started yesterday, and I started this 2 weeks ago, and I also wrote my little my own CDCL implementation like a few days after that. So I'm outside of the bounds to be in the jam, but I'm not taking the jam time boundaries too seriously because this is a topic I'm into. So I was kind of inspired by the jam, but I'm operating entirely outside of the suggested parameters of the jam. So am I doing the jam or not? I don't know. But I do plan on learning this for a little while and then doing a series of videos on the theory, and also if I come up with a good implementation, how to use my library or something. All right. Okay, so that might be an interesting file a little bit. There's a lot of stuff here that's setup and handling that is not that interesting. And I don't want to get too bogged down in it as I go, so I'm kind of running through it quick. But let's see. So we got a stream buffer thing that's coming from this GZ file input stream. And they're constructing one of their stream buffers, which is just going to be, what is this? Dereference to get a character from the buffer, position plus plus to increment the position to get the current position. You got you really had to, okay. I don't know. It's fine. They're probably doing some incrementally unzipping a file as it goes kinds of logic in there. I don't think that's probably a good idea. On a modern computer, you're not likely. It you're not likely to get any benefit out of switching back and forth between two different tasks. In order to keep the memory usage small, you're more likely to get a benefit out of. You're more likely to get a speed benefit by getting all of the memory for your task loaded up at once and then doing the task all in one go. If you can fit it in memory, like why would you not? Why would you not take advantage of that? But yeah. Anyway. Okay. So yeah, here we're seeing things like, okay, see, this is a comment, skip the line. Skip the line is a helper function, not a, what is B? So they've got maybe multiple of these stream things, but is EOF, they are repeating until they find a new line character. Okay, got it. Sooner or later, presumably we find the P. There it is. So the P, don't know what eager match did, probably took PCNF. So unexpected character star in. Okay, so they only support CNF. That was the main thing I wanted to get out of looking at all this setup. I'm not seeing any sign here that there's any other kind of Dimax file I need to watch out for. So we're just looking at parsing these CNF files. And then it's going to go, okay, how many variables do we have? 100. How many clauses do we have? 160. And now that we've found that, we are ready to start parsing in those clauses. So then it goes read clause, and that's probably, going to be pretty straightforward. Although actually, weirdly annoying. So, okay, got it. Absolute value, right, parsed. So we parsed an int. We make sure it's not 0 because that would be an error. And oh, no, this wouldn't be an error. It would be the end of the clause. So if it's a 0, it's the end of the clause. If it's a non-zero, then we take the absolute value of it because we can use negative versions of our variables to represent their negation. And then -1, just so that instead of being 1 based, our variables are 0 based, I suppose. And yeah, MiniSat is from 2005. I'm reading this fully aware that it's from 2005. I'm not if anyone who worked on it or admired that in 2005 hears me sounding critical or annoyed at it, I hope that you will understand that I would have written this code if I would have written code this way. I should say I'm not responsible for this. I'm not claiming that I would have done it this code as good as they did or anything. What I'm saying is I would have written code this way at once upon a time too, and it's just I am attempting now to make something that works as well as this but in a very different style, and so I have to pick apart all the style stuff to make notes in my head about what the program is doing. And yeah, for sure, parsing the CNF isn't the bottleneck. I'm reading this mostly because I wanted to see what the MiniSat supported. So it only takes in CNF. So I wanted to ask, since I've got you here in the chat babble, the CDCL solver I looked at and now this one both operate directly on the CNF. I find that a little surprising. It feels like you would at somewhere we need the conversion, and I'm sure it's not like that expensive or anything, but somewhere we need the conversion from a plain old SAT like Boolean formula to the CNF, and none of these ever seem to include that. At least so far this has not included that. So is it pretty common for those to not be bundled in? And do I need to like look at another helper to get that, or is that like gonna be a helper somewhere in MiniSat? Do you think, or what? That's okay. So the conversion of the formula into the CNF is a completely separate, difficult problem, is what you're saying, which makes sense because if you just run the simplest possible algorithm, you do generate a lot of variables, but I could very easily imagine there being ways to notice patterns in the general formula and take advantage of them to make simplified CNFs, which is probably why it's a research topic on its own. What do I need to look up? Like, where's a project that I should go to for getting started on that half? Because I want to do Boolean formulas as my interface. So Babel says going from Dimax to CNF is included in MiniSat, with some optimizations of the CNF as well. But taking an arbitrary formula and making a CNF is actually surprisingly hard. You mean it's surprisingly hard to do like an efficient one, like one that makes a good CNF out of it? Because I thought there was a pretty standard, like, I thought there was a pretty rote algorithm. But if you're saying like, yeah, but the rote algorithm is impractical and has to be highly worked upon, that makes sense. Oh, here we go. Yeah. Yep. Okay. Makes sense. Um, I will put that on my list of things to look for. Okay. So let's move on now. I've got what I wanted out of that. They've now built the one thing I skipped there was when we were looking at parse, and it was parsing, presumably somewhere in here was parsing the clauses, right? Was that over here? They were parsing the clauses. Read clause, lits dot push, right? So that we have this lits thing. Let me pay attention to that for a minute. Lits gets a variable pushed on. Where did that come from? No, read clause here, lits. So lits is a local. Okay, I see. So we pass in the literals. It clears the literals and then fills them inside here. So it's like rewriting that literals there, and then it is doing an add clause onto the solver itself. Is that right? Yeah, there's our solver. Okay, give me a sec. Okay, Babel, that makes good sense. Thanks. I'm good. I'm excited to learn about that part. I was under the impression that that conversion, while it was important, was relatively like easy to just plug in, like a starting point, and then the rest of what you could do was optimization. But it sounds like you're emphasizing that as possibly one of the most important parts of like getting good results out of a SAT solver, which is good to know. Go away. Okay. Mm-hmm. 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 Again, no idea why we're doing that, how that even works on Windows. Simplify. Description. Simplify the clause database according to the current top-level assignment. Currently, the only thing done here is the removal of satisfied clauses, but more things can be put here. Interesting. So, simplify is going to remove satisfied clauses. Remove satisfied clauses. That way we don't iterate them over and over again while we're... So, as a reminder, the main algorithm here is like, we're going... how do I want to describe this? We're going... let's say we make a guess. We propagate constraints. So, our guess might force other variables into certain states. And while we're propagating constraints, we have to loop over all of the clauses. And some of the time, we might find out a new value for a variable, and then we have to start the propagation again from the beginning, because with a new variable, some of the other clauses that previously weren't giving us any information might start giving us, they might start being constrained down enough to do something for us too. So we have to keep running this. Propagate constraints is basically internally, this means like an iterative loop that does scan the clauses and look for a constrained clause, and then if you find one, update the variables. So if they are taking out, if they're removing the fully satisfied clauses, they're just speeding up the process of scanning over all the clauses. Yep, makes perfect sense. So Babel says, the how do you even say that word? I haven't said it out loud yet. The Satan, is that Satan? That looks like Satan. The Satan transform. He says that you can just plug in, which, right, so obviously as long as you find a correct translation from the formula to CNF, you're good to go. So if there's a translation that always works, then you are able to do it correctly. The problem being that if your problem doesn't translate in a way that leads to like a nice, simple... If you start blowing up the number of variables too quickly, you are going to run much slower, and so the research goes into using domain-specific pre-processing things, probably, to notice patterns and use them to make translations that are less nasty. Satan. Okay. Propagate. If not okay, propagate equals CR. Return okay equals false. Okay, this looks like the propagation I'm already familiar with from my last code read. Trail, huh? What is trail? Well, it's empty, so nothing happened. So this is not the same. It's probably just an optimization of some kind, but queuehead is not less than trail size. Let me go and read solver more carefully. Do we have a solver H? Good, thank you. Okay. 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 Solver state, trail. Here we go. This is a long. Okay. Trail. Assignment stack. Stores all assignments made in the order they were made. Okay, perfect. That's the thing I was thinking of doing. That makes sense. So what it's talking about is in the one we looked at last time, and in the way I copied its structure before I had time to think through how I would change it, what it was doing is it kept a bank of variables, right? We got so we have 100 variables. So it's got a bank of these things, and initially clears them all to unassigned, right? They all are free to take on either the true or false value. And then it would pick one of those variables, pick an assignment for it, and that would form a guess. And then it would remember the order in which it made guesses using a decision counter and put those decisions into the assignments along with the values. So if I say, okay, variable 10, I want to guess that it's true, and this is my first guess, it would go to the 10th slot, put a true into that slot, and put a 10 into the guess counter for that slot. And then if I make a second guess, okay, variable 20 I think is false. That's my second guess. So it gets variable slot number 20 gets the false state, and it gets guess number or guess counter of 2. If I then later learn I need to roll back to the state where I hadn't made any guesses yet, I need to roll back to before guess 1 happened, then you would scan all the variables, and anything that had a guess number or a guess counter greater than or equal to 1, you'd unset that and clear it out, right? You'd set it back to unassigned. What this is saying is, instead, whenever we make a guess, let's keep a stack of them. And so when we want to undo our guesses, all we're going to be doing is popping to a certain point in the stack. And there are a couple of reasons why to prefer that, but that was sort of the same thought I had. So I'm already on board with that idea. Let's see. Separator indices for different decision levels in trail. Right, so when you make a guess, I guess that variable 10 is true at the beginning of my algorithm. You might then have propagation set some other variables, right? So it might turn out that variable 11 has to be false if variable 10 is true, right? If variable 10 has to be false if variable 11 has to be false, just because variable 10 was true, I don't need to make another guess yet, right? I'm still on guess number 1. So even though guess number 1 was just assigning variable 10 to be true, the propagation of constraints means that during guess number 1, variable 11 was false. So that's also at guess number 1. So what this is saying is we want to keep track of the ranges inside that assignment stack. So as we're adding assignments, some of them are guesses and some of them are constraint propagations, and there are ranges within that stack that are all part of the same guess. And so this is giving us the indexes into the stack that mark the separate guesses completely. Current set of assumptions provided to solve by the user. Interesting. So I assume this is just so you can create a formula and then assume a few values for variables that you don't want them to be, you don't want the solver to treat those as things they can roll back and try a different way. You say, hey, I would like you to work on it with these variables assigned in this way. Now the rest of this, I'll have to come back for and learn more. List of problem clauses, list of learned clauses. Cool, cool, okay. Where are we? So we're in the middle of propagation. Propagation didn't do anything because our trail size is 0. And that makes sense. So remember, what is the trail? The trail is the list of all of the assignments we've made so far. So in the other solver, in order to do propagation, when we would look at a clause, and we would say, is this clause constrained? Is this clause close to being resolved? Are we at the point where there's only one variable left and it has to go a certain way in order to satisfy this clause? In order to figure out the answer to that question, we would then look at each literal in the clause and scan all, look up its value in the bank of assignments. What this is doing is saying, hey, look, your trail, if it's empty, there are no assignments, so there's nothing to propagate, right? Propagation only makes sense when there are assignments. Let's read more of this, because I'm curious if the rest of it is the same as what I would expect, or if it starts to look different. P is in queued fact to propagate. So P is the fact to propagate. P is queue head plus watches dot lookup P. So what is watches and where does that come from? What is that? Is that something living over here? Watches, watches, here it is. So the watches variable is an OCC lists, oh god, okay. So we have a template with 4 parts. We're gonna need to go look up that structure to learn how to interpret this, but let's read the comment. Watches lit is a list of constraints watching lit. It's a list of constraints watching lit. Okay, let me read the code right here. P, watching lit, watcher. Okay, so it sounds like we have all these different literals, or all these different variables, right? Technically, watching lit. But this is coming out as a literal. Interesting. So this is coming out as a literal, which means maybe the true and false versions have separate watcher lists, which I guess could make sense depending on what this is doing. It could be that it's saying, hey, if this thing is false, we don't learn much, but if this thing is true, it constrains a bunch of stuff. Right? I don't know if you've ever done a Sudoku problem, a Sudoku puzzle, and there was a point where if a certain variable, or if a certain square in the grid went to, if this was 9, it would force all the other things to be 9. But if it's not 9, then there's a lot of other ways I could make the 9s work, right? But that's the same sort of, that sort of thing happens in constraint problems, right? So there's one side might be, if that's what the watchers are kind of implementing, a logic that says, hey, when this thing goes true, then all of this other stuff has to follow. But if that thing goes false, the stuff that follows is totally different. It might be less, might be more, but it's not just opposite. So we can't just have the true and false version of the variable linked together if we're trying to accelerate that way. That's my guess. Let's go and read actually about the OCC lists real quick, just to see what that's about. It looks like it's going to be complicated, but we are digging in. So A class for maintaining occurrence lists with lazy deletion. Occurrence lists. Got it. This is short for occurrence lists. Now we have a k, vec, deleted, and an mk index type. We need to decode the template now. Can I actually, are there a lot of, okay, so we have occurrence lists on literals and we have occurrence lists on variables. That's why that is templatized. This is a list, let's see, vec. So it wants to be able to create lists of different types, and it's doing that through, you pass in what structure the list will behave like. Here, watcher deleted. This is a okay. What are you thinking here? A deleted, I might need to look at what a watcher deleted is to appreciate this better, but it's like living inside the OCC list. It's something about lazy deletion. MK index. What do we do with the MK index? Oh, I see. So we have these int maps. Don't know what those do. Occurrences, dirty, dirties, deleted. Okay. Okay. So K, reminder, K is the thing. We're making lists that attach to keys. These are the keys, right? So in occurrence lists, right? Because this isn't an occurrence list. It's an occurrence list is a thing where you put in the key, that could be a literal, that could be a variable, and you get back out a list. And the list is a list of this type. Right, so this is what defines what a list actually means. And then somehow we have, I don't know what MK index represents exactly, but somehow these int maps are involved. So you could imagine if I give you a key, and this maps to this, but what is the MK index? Int map. What do you, there's probably some optimized data structure stuff happening. So it's not necessarily the most important for understanding the core structure of the algorithm, but I want to just see like what the data structure optimization stuff they're thinking of is. Okay. Okay. Int map. Okay. So that's for setting the index. This is some wild stuff. What I'm getting from this is probably their it seems like they're trying to let you use different integer types for the make MK index thing or something, maybe. I'm not sure. I'm also not sure, like, it's always hard to tell, like, is this might be critical for optimization if, like, hey, an index of 8 bits makes a big difference, but it's hard to see any of it. It's like hard to see if that's why it's that way or if there's something else going on. Okay, let's see. Operator K. So that, you put a K in, you get a V out. Index. Oh. Index. K in. Size, type name, vec t, size t. So we're returning t and we're casting it to an integer. So that k is some kind of integer. And this index is like a functional kind of thing. So like this here, this type. Look at this. Okay, so this doesn't contain any data, right? This is not an integer type. It is just a struct whose purpose is to contain this function so that you can call with the index thing in order to implement the cast that gets the correct index type from the key type. I think maybe that they're trying to bury their casting so deep inside of a template system that they don't feel dirty for using an integer cast, because there's a whole culture in C++ of like thinking of like, look, we should move towards being more strongly typed and not casting. Casting is a sign of bad design. And there's a whole other thing of like achieving type safety through templates. And so if you thought casting was poor type safety, and you thought templates were a mechanism for increasing type safety, burying your casts deep inside of a template nest could make you feel safer. And unless I'm missing something, that's what this looks like. Like I'm not seeing a lot of sign that this does anything besides carry through the type system a notion of which integer type to cast to, which is confusing because it's a lot of code for achieving nothing. But I could be wrong. There could be something I'm missing. It's hard to tell. Begin end. So here we're looking at the sort of iterator at bounds if we want to loop over the map. But really, why? Why not just use the vec? What are you getting out of the K? Out of the reserve? Grow to insert reserve that much operator square bracket key value insert. Okay, I think I get the idea. All right. Brett, that sounds fun. Looking forward to see what you find. Okay, so I'm not entirely sure I get the idea of what that's doing, but basically if we go back to looking at the occurrence list, basically what we got here is the int map takes k type integers. This is an integer type, and maps those to these types here. So it maps it to, in this case, a vector type, and in this case, a char type for the dirty. That might be a 1-byte Boolean or something. Let's take a look at how dirty gets used. If dirty, yeah, I think that they're thinking of it as a Boolean. Dirty equals 1. If dirty index equals 0, dirty index equals 1, dirties.push index. Okay, dirties is a list of those k values, and so what we have here is two different data structures tracking dirtiness. One is a map of every k value to a Boolean of dirty or not dirty. The second is a list where you can start at the beginning of the list and go down the list to see all the things that are dirty. And so we have those side by side, presumably because sometimes we want to scan the dirties, and sometimes we want to check if something in particular is dirty. That's what would make the most sense. And whenever we init an occurrence list for a given index, we reserve for that index. I think this is just a fancy way of saying we have an array of arrays with some, like, with this whole int map thing. Or we have an array of these indexed by these. I don't know. Maybe there's something relevant to the make index if I actually go, the MK index, if I actually go and look at where it's not using the default. Let's take a look at that. Because you could imagine them putting something more interesting in there. Index lit. There we go. So that might be worth knowing about. L.x lit struct lit. It has that same operator that the other one has, and it's saying, how is this not just the same thing? L.x, that's what's different. How is the lit defined here? Okay, got it. Oh man, okay. So yeah, this is just an integer, but they have to access it through the field X because it's not just a type def. They wanted to make it a thing with some object-like functions in it, and so it can't act as an integer all on its own. And they didn't think that casting it to an int for free was a good idea for some reason. Okay. All right. So looking again at occurrence lists, we have an occurrence list is a thing which takes in a literal. It spits out for that literal a vector of watchers, and it keeps a dirty list and a dirty bit map and we don't know what a watcher deleted is yet. What is this part doing? Clause allocator, you make a clause. You give the watcher. When you call this on a watcher, yeah, so the watchers themselves, I think the cref stands for clause reference. Just living inside of the solver. Yeah. Okay. we are getting somewhere, even if it looks real rough and painful, and it is rough and painful, but we are getting somewhere. So what I want to do is go back to stepping through code. I think I've seen enough of that. So propagate, what would this do? So it looks up the vector of watchers from P. So this is, okay, this is where we can start making sense of it. I don't know where Q head is getting handled. Like, it seems like that should get cleared to 0, but it's not. Q head lives inside the solver state. Head of Q as index into the trail. No more explicit propagation Q in MiniSat. Okay. So we have the trail and we have the Q head, which indexes into the trailhead. More occurrences of Q head. It gets initialized to 0 at the beginning. Revert to the state at a given level, keeping all assignment at level but not beyond. Right. That is a part of this that I'm still confused by. So the CDCL solver did this too, where when it reverted, like it would say, hey, we want to revert to level 5. It would revert to everything after level 5, but it would keep the level 5 stuff. And it always seemed wrong to, like, I always was confused by that. It seemed like, shouldn't it be rolling back level 5 as well? That's the way I wrote mine, and mine works on the cases I've thrown at it, but it might be that it's unnecessary or something, and I haven't really appreciated why. Or it might be that the thing I was reading was wrong, that this is right, but they're going to call it differently from the usage side. I'm not sure. But besides that, so when they're rolling back to level 5, they're keeping level 5, but dropping everything higher than level 5. And then they are using remember how we talked about how there's the trail that they have, it's the stack of assignments, and then they have indexes into that stack to track where each guess occurs. So they are now going into that, this thing is those spots where the guesses occur within the stack, and going to a certain level there, and using that to roll back their Q head. So the Q head now lives on the stack at the place where the guess from that they've rolled back to starts. Okay. So Q head doesn't necessarily start at 0 all the time. That's interesting. The number of props. I think that actually makes sense. I'm thinking over it in my head again, but if you're trying to not do any extra iteration, the only place where new propagation should even be possible is on most recent guesses, right? Like if a clause is not touched by the most recent guess, then the constraint propagation shouldn't even have any effect there. So what is this doing? This is grabbing those watchers from the watches, and that's the occurrence list. So we take this literal and we say, hey, do we have any watches for this particular literal? And we're probably, let's see, ij equals ws. So, okay, this is interesting. End equals I plus ws size. Okay, so this is probably the beginning of the iteration. This is calculating where the iteration would end. This is the end condition on the loop. We don't have any increment built in. Try to avoid inspecting the clause. Lit blocker equals I blocker. If value blocker equals true, j plus plus equals I plus plus continue. I don't know what that means. It's interesting to see. So it looks like the J is probably an iterator that trails behind. This looks like a similar pattern to what you get in something like a merge sort, where you have two iterators. One of them is scanning ahead. It's sort of like a read pointer, and the other one is trailing behind, and it's like a write pointer. And if they're in lockstep, then read is just going to write to the right, and nothing will happen. But if the read pointer gets ahead, then as it's writing, it is actually overwriting old stuff that it didn't need to keep. So it basically chooses to write back those things that it needs to keep. In merge sort's a little different because it swaps them rather than obliterating them. But yeah, it's a pattern that shows up in a couple different ways. Make sure the false literal is data 1. CREF. So I, as a watcher, I don't actually know if I know much about what watchers do, though. But I think I see what's happening broadly. There's little optimizations in here that I don't understand yet, but the watcher isn't that... I know it's right here. Right? Here it is, watcher. It's got a CREF, a blocker, and CREF. I should know what that does. I should know what that means. Type def, region allocator, ref, CREF. Region allocator. I think that this is an arena, probably. Maybe some kind of pool. Memory for clauses. I want to see the region allocator. Yeah. Memory, size cap. Wait, so make this a class for better type checking? Yikes. Okay. What do we got? Yeah, so it's grabbing a million spots for whatever a T is. It's an arena for a fixed type. It can only allocate one type, but it's just going to push them onto an array. Some moves. You gotta always do your moves when you're doing object-oriented programming. Alrighty, so okay, got it. So what we have is this allocator does two things for you. One, it works like an arena, but instead of returning pointers to you that you have to handle, when you allocate, it returns a ref, and a ref is just an integer. So this way we can get 32-bit references instead of 64-bit references on a 64-bit machine. Does that make sense? So to say that again, a pointer on a 64-bit machine points straight at the thing we want. This allocator is saying, let's make the handles that we pass around to refer to clauses 32 bits. And then this class is here to implement both the allocation and doling out of those references, as well as the mapping of those references back to the pointer for when you actually do need to use the memory. And so it's got things here for, like, you put in the reference and it puts out the pointer. You put in the pointer and it puts out the reference, so you can get back and forth. You allocate, you get the reference. And it doesn't free. Or rather, when you say you want to free, it just increments this wasted counter, so it can keep track of how much memory it grabs that it didn't free, because it doesn't free. Okay. All right, so that's what our region allocator is doing, which means that these crefs are clause references. They are 32-bit integer indexes to a clause. The region allocator is there to... Right. Region allocator is just there as the actual implementation of the allocator. The clause allocator, clause word 32 size, int size has extra return clause, size of lit times size plus int has extra. Divided by size of uint 32. So divided by 4 is what they mean. Word 32 size, clause word 32 size. Trying to figure out how big of a chunk of memory you need for a clause structure plus an array of literals, where the size of a literal is this, and then the number of literals is size, and then has extra is possibly one more. And then dividing by 4, because we are not counting how many bytes, but how many 32-bit words we need for this thing. Probably to ensure alignment or something. So when we allocate, we get the cref, and then we allocate the clause into the pointer there. Or we construct into that. So this is doing the allocate clause word size ps.size. So did I miss something when we're doing the region allocate? Interesting. So the allocate function takes in a size and right, it's an arena. So they're not all, while it's typing the things it returns, they are not all the same length because we're packing the clause in with other data that the clause depends on. Okay, fine. Okay. So I know what a watcher is because I know what a cref is now. I know what a lit is. So a watcher is a clause reference. It's a reference to a clause, and it's a reference to a literal called the blocker. And up here are watchers. Where is that? Down. It's down. That's why I'm getting... Our watches is a map that you put in a literal, and out pops a list of watchers. Each watcher, popping back over here to the propagate function to understand it a little better. Each watcher is visited by this loop with I being the iterator, make sure the false literal is data 1. The false literal, false lit equals. So P is what we're propagating. P is the fact we're propagating. We are then going to look and see everything we know about the watchers. If we have a blocker, then that particular watcher is not applicable, and we hold on to that watcher for the future. Make sure the false literal is data 1. False lit. C0. So where is that coming from? CA is... Who is that? Who is CA? Okay, so CA must be how we... This is the clause allocator. And this is the clause reference, right? So our watcher has a clause reference. Okay. That clause reference allows us to get to the clause. Okay. What is P? P is the fact we're propagating. So this is the opposite fact. This is the false, the negated version. So if I have variable 10 in the positive form in P, false lit becomes variable 10 in the negative form. If I have variable 10 in the negative form, false lit becomes variable 10 in the positive form, right? It's the negation of whatever P is, which can be the positive or negative of a variable. Okay. If C0, so C is the clause, is false lit, C0. Okay, let's go and look at what the clause does when you index into it. Okay, here it is, square bracket. Must manually call calc abstraction afterwards for subsumption operations to behave correctly. Brilliant. We'll find out about that. Okay, so the square bracket on this thing is indexing into... This is basically an array, right? The clause is where are its members? Surely it has a member or two. It's not inheriting. Oh, there we go. Header, data. Got it. So the header is a bit field that tells us a little bit about the clause. Some global info about the clause. Or some info. This is per clause info. And then the data can either be a literal, a float called act, in UN32 called abs, or a clause reference called rel. Okay. So we don't know a lot about that then. That's surprising. That's a lot more than I expected. I would have thought that this was just going to be an array of literals, and instead what's happening is we have a packed, all of these are probably supposed to be 4 bytes, right? Each of these is a 4-byte thing. So we have a packed array of 4-byte things, but we don't know for sure which type it is. There's 4 different types that they can be. Probably usually literals. That's what I think is probably happening, but these are probably other, like this might be for a heuristic, this might be for an optimization where you want to treat it as a variable instead of as a literal. This, I don't know what this could be, another optimization, another data structure trick. There's a lot there. Okay, so an array of 32-bit integers, or 32-bit value. I can't even say integers since float is in the mix. Of an array of 32-bit values, and when we use the square bracket on it directly, we're just manipulating that array. Okay, that's what I wanted to see. Now, if I come back over here, how much does that help? If I'm looking at a watcher, and I look at that watcher, it's saying if the first literal in this clause is the false version of this lit, move it over 1. Move it to the next spot over. And then assert that that's where it is. So okay, so by this point, it is definitely the case that the false version of P is at position 1, or else it would assert. It's possible before we got there that it was in position 0, but after this, if it wasn't in position 0, then it was already in position 1, right? Like, that's something I can conclude from this. Which means watchers only exist when, like, each watcher either has a blocker or this is true. That much I can be sure of. So then it checks the 0th watcher. If this watcher is, then it checks this part of the clause. Remember, C is still our clause. Watcher CR first. So if the 0th watch is true, then the clause is already satisfied. So we're going to look at lit first. Right, so we're constructing a watcher. The watcher watches the same clause we've been analyzing, and the new blocker is that first literal that is, well, it's just the first literal. If that's not the same thing as the blocker from up here. So if the watcher we're starting with, because remember I is already a watcher, and we read some stuff off of I before we incremented it. And one of the things we read off of it is its blocker. So if the blocker from I is not matching the one we're on, and if this evaluates to true, then we're writing out a new watcher to J. So remember, J is our right pointer. Here we're not copying over an existing watcher from later in the array to here. We're constructing a new one and putting it here. But if we got this far, we know there's space because we've already incremented I. And as long as each time we increment J, as long as we only increment j when the same number of times as we increment I or less at all steps, it will be okay. You don't want to get into a place where you're writing j several times before you read I, because then you can get overwrite where your new stuff replaces what you were supposed to read. But as long as it's either I runs ahead and j occasionally steps, or they're in lockstep, or they're guaranteed in some way, it's like I steps forward and maybe j steps forward, which is what we have here, that's all fine. Look for a new watch. Okay, so what does this do? Okay, starts at 2, goes over the size. So we're looking at the rest of the things, and anything in there that are not false. So the rest of the literals in the clause. So we had a clause, special treatment for the first two. One of the first two had to be the false version of the variable, or of the literal we're propagating. That makes sense, right? So why does that make sense? Well, in propagation, what we're looking for are clauses that are so close to becoming fully false that they only have one variable left, and that one variable is still unassigned. So if I have a clause with a couple of falses and one unassigned, that one unassigned has to go true or the whole clause comes out false. So when we're propagating, we're looking for clauses that are in that state so that we can make the logical deductions about which literals we can use to force variable states, right? Or which clauses we can use to force variable states. And all of this is just a data structure for accelerating that lookup in the way you would think of. It took a long time for me to get there, but I've seen what the code is talking about now. The code is saying, hey, when we go to propagate, instead of scanning the clauses and then testing if any of them are at the point of, like, or at the critical point, let's call it. If any of the clauses, instead of scanning each clause and testing each one independently, are you critical? What it's doing is it's saying, hey, why don't we scan these by variables? So we have a variable that we've just, technically by literals, we have a literal that we've just asserted. So like, hey, variable number 10, x10 is true. That's the assertion. And then we're looking through, we have attached to that, if x10 is true, then we are looking at all the places where the false version of x10, so not x10, right? Any clause where it says not x10 is interesting because that clause might be constrained now, right? If it wasn't critical before, if that clause wasn't critical before, when we go to process the fact that x10 is true, all the clauses that say not x10 are now clauses that might have become critical. Okay? So, what this part is doing is looking at that list of clauses, right? This list of watchers is basically that list of clauses that might become critical because they contain a false version of the literal we are propagating. Now, why that literal has to be in spot 1 or 2, I'm not entirely sure. But that's somehow works out. We'll get there, maybe. So we've looked at our clause. We haven't quite figured out what a blocker is. I have a sense of it, but I'm not sure. We know what this is doing. It's saying, hey, check to see. I don't know why we can assume that it's in one of the first two spots, but check to see if the false literal is in this clause, in the right, and make sure it's in the right spot. Then we check to see if the 0th watch is true. I think it means if the 0th literal is true, because it grabs this and checks if it's true, and if it is, then it saves the watch. But either way, the point is, it then continues because, again, we're looking for critical clauses. Clauses with a true literal are definitely ones we can eliminate. Look for a new watch. So here what it's doing is it's scanning over everything besides those first two special ones. Don't know why they're special. Don't know what's going on with that. But it's scanning over the rest. And it's saying, okay, if the value of any of these literals is not false. So if they're false, that means we've assigned a value to the variable, and the literal is coming out false. So that could mean that we're looking at variable x20, and that x20, we're looking at the positive version of the literal, but the x20 variable is false. Or it could mean we're looking at the negative version of the literal, and x20 is true. Either way, the literal is coming out false. And so then we move that into C1. We copy the false lit into CK. So now we're swapping. Do you see that? The false lit is the thing we assert. We know that's in C1. We overwrite that with CK. Right? And then we save the false lit we were holding on to into CK. So we've swapped C1 and CK effectively. And then we go to the watches map. And we push a new watch on. And the new watch is W. And W is the watch that we saved up here. How does that make sense? Go to next clause. Next clause. So this is a continue out of the outer loop, basically. The reason they have to use a go to here is they're inside of this loop. They want to end this loop and continue inside this loop at the same time. That's all that is doing. You could put a go to next clause here, except continue also does the same thing. It's the same thing, right? Okay, so why does this part make sense, though? Why are we taking a watcher who is looking at C0 as the blocker and CR and putting it onto this? Why, now that the false lit is over here in CK? So a part of what's happening here that's interesting is when a blocker happens, we are throwing away watchers. Watchers get processed and consumed up. They're not sitting there forever. This isn't a static data structure for accelerating navigation through the structure of the clauses. This is a list of tasks, more like. It's a list of work to do. We're processing them. Sometimes we look at them and say they are blocked and keep them around. Sometimes we consume them by saying, oh, this one, yep, this looks like it worked. It's in the first or second slot, and we're good to go. So this one is getting processed. And then it's gone. It's gone, right? The watcher is gone here, but we're still processing it. So then the processing happens in this part. And the first part of processing is to construct the new watcher that we might want to save. And that new watcher has a blocker, right? So that we bail if this thing is already true. So we're just checking the first one for some reason. If that one's already true, we're bailing. And we're saving this watcher in the list of watchers for P, right? So the list of watchers for P remains the one we're modifying, and we just save that watcher there. But if this is not true, then we push the same watcher. Then we look to see if there are any unassigned variables later in the clause. if there are any uninitialized variables, or literal, like if there are any literals in the clause whose variables are uninitialized, then we take the first one we find, we put its its negation gets the watcher. That is just mind-bending. I'm gonna need to draw a picture of this. I'm gonna press on for now and make a note that I want to draw a picture of this data structure more carefully. I think a picture of this will help me a lot to understand the significance of saving a watcher onto the negation of the first uninitialized variable. But if I had to take a guess, it's something like, remember we are saying if this is in this clause, right? So this is still about the same clause that we started. Yeah, it's all about the same clause. The negation of this would move this clause closer to being critical, right? So if CK is in the clause, which it is, say that's variable 20, and it's unassigned, then if we decide to make variable 20 false, and this was the true version of variable 20, or like the positive literal of variable 20, then we move then the clause will become closer to critical if we decide that variable 20 is false, right? So the positive version appears in our clause, which means it's the negative value of that variable that could move us towards being critical. And of course, if this is the negative version, then this becomes the positive version, and the same logic applies, but flipped, right? Okay. Did not find a watch. Clause is unit under assignment. I think this is jargon that I'm calling it critical. They call it unit under assignment. I don't know if Babel is still with us, but I'd love to know if there's a way to like get the terms sheet of all the jargon that I should be using for this. But it looks like unit might mean the idea of a clause that is maybe almost, like that I'm calling critical, like almost fully false, but not quite. So we know, because we got this far, we got past this assert, this variable, this literal is false. We know that the first in the clause is not true. So that doesn't mean it's false. It could be unassigned or it could be false, right? We didn't stop here, which means we didn't find, which means all the rest of them are false, right? So if we get past this, then everything in there is false except for the first one. If we got past this, the first one isn't true. If we got past this, then everything else is false. And so we end up with the first one being the only possible hope, but we haven't actually figured out whether the first is false or not. So if I could step through this, that would also help. But I think I'm getting what's happening. This must be where we've identified a conflict, and so we wrap up by saving the rest of the watches that we haven't processed, and we'll probably go on to conflict handling. Otherwise, we call unchecked in queue. I don't know what that means, but presumably we have determined that first needs to be set to true. And so this would be the thing that propagates the value for the variable that would make this critical clause satisfied. And no conflict here. So let's see. Um, number of assignments. I imagine that's 0 to begin with. No, so that doesn't happen. Remove satisfied clauses. Remove satisfied. So we check if the clause is satisfied. Remove clause CSI. Trim clause. Oh, they removed the false variables. Look at this. If this is false, so if this is a literal in the clause, it skips over those first two, which again I don't entirely understand why, but the first two are kind of being used as like slots for a special logic as things get processed. The rest here is going, hey, are any of these literals false? And if so, just overwrite that part. We don't need to keep around false literals in this clause, apparently. And then, yeah, it shrinks the size of the thing. And it only does that on the learned clauses. Interesting. No, my mistake. It does this on both types. That seems crazy. But maybe we only run simplify at the beginning or something. If we were running simplify all the time, I think we would be overwriting necessary information. But if this is a simplification that happens at the beginning to say, hey, the user has given us some formula, but they've also set some of the variables, and we're not allowed to even modify any of the things the user set. So let's run a simplification pass. Anytime we have a formula and a partial assignment to the variables, we can combine those to eliminate all of the partially assigned variables, right? And so any variable that's any clause that is already true can go away completely. Any clause that's not already true, all of its false members can be taken out because they can't be modified anyways, and so they won't help us make the clause true. They're not useful information. And what's left is either you have an empty clause in which the whole thing is impossible from the start, or you have a list of clauses with just the unknown variables that the solver can actually modify in the first place. That's probably what this is about. Don't know about that stuff. Gonna just step ahead here. Okay. Give me one moment. And we're back. So, moving forward, we have a dummy. What are we doing with solved limit? Assumpts, copy to assumptions. No idea which way we're copying here, so let's take a look. Copy clear, copy grow to size. So we're the parameter is the destination. The object that is on the left side of the dot is not being modified. Okay. So assumpts, which I believe is empty, gets copied to assumptions, which is a member of the solver. Okay. Print stats. Wait, that's it. The program is done? Yeah, that's it. The program is done. Okay. So I missed the solver part. Huh, how did we parse the file, we print some stuff, sig term, we simplify, solve limited. That must be where the solve happened. There it is, look at that. Okay. So what it's saying is set the assumptions to set there to be no assumptions and then run the solver. So we don't care about this part. We want to see solve underscore. Okay. So these are zeroing out things. So we have an empty model, empty set of conflicts. Don't know why that would be not okay. Can I go and see, I want to see solver H again. So model. Okay, so that's like what I learned from the CDCL solver. Model means the way the way we're assigning values to all of the variables in the problem. Okay, that makes sense. That makes sense. So, all right, what are you folks doing here? So we have an L-bool, lifted booleans. So this is probably to implement the true, false, uninitialized logic. Let's learn about this piece of the program. So So they are initially zeroed out. If you give it a Boolean, it just puts the negation of that Boolean into the value. So true, which would be a 1, you get a 0 in the value. 1, 0, which would be false, become a 1 in the value. If you do nothing, you get a 0. Okay. Operator and. What is this? Wow, okay. The FF7. What is this? Wild. Okay, let me try to read this very step by step. Equality between two things is defined as if they both have the high bit set, then they're equal. If what is that? I assume that the not must bind. Man, this is operator precedence nonsense now. So it's not a chain of ands, right? If it were, this is always a 0 or a 1, which is always a 0 when you and it with a 2, which would always be true. Wait a minute. That's an and that's an and that's an and. So this is this anded with 2. Bit ORed with a 1 if the values are exactly equal. And okay, so if this has a 0 there and they're exactly equal, then they both have a 0 there. So what this is trying to say and is that if they both have their second bit set, then it's true. If, regardless of their first bit, If they both do not have their second bit set, then they are equal if the whole value is equal. In other words, if the first bits are equal. So equality in the first bit means they're equal if they're both 1. But if they're both 0, then equality in the first bit takes over, right? Or I don't know if I said that correctly now that I listened back to what my brain heard me say. If they both are active in their second bit, then they are equal. If they are both non-active in their second bit, then if they are equal in their first bit, they are equal. If they disagree in the second bit, they're not equal ever. If they agree in their second bit, but it's a 0, and then they disagree in the first bit, they're not equal, right? So there's something going on there. It's a little bit complicated, but hopefully that makes sense. They're not equal if, okay, and so we just implement not equal through the equal operator. That's what they're doing here. They're doing this to invoke this and then nodding it, so it's just the negation of that. We XOR them. We XOR an L Boolean with a Boolean by modifying just the first bit. Okay. We AND two L bools by, we bit shift up this value by 1 and this value by 3. And then we're taking 2 bits. Okay, so this is a pattern of this is a set of 2-bit patterns. This is a lookup table. This is a bit lookup table. That's why it looks so crazy. Okay. Let's translate so I can interpret this. What we're looking at here is we have v1 and v2 as our parameters. This is an implementation of which function and. So we're talking about lifted and we're going to output a U8. Okay. We have a lookup table that looks like this. And now we grab something out of the lookup table by shifting the lookup table bits down and taking the low 2. So the result is the lookup table shifted by some n and with 3. So that gives us a new 2-bit value that we can return. Now we just got to look at how they're calculating n. So what I call n, they call select. That's something like this. N is v1 shifted up by 1 bit, forward with v2 shifted up by 3 bits. Okay, so there we go. That's how I read the code. And the other thing that would be helpful here is to see the different values these can take. So v1 and v2 are 2-bit values each. So when they shifted, whoops, my mistake. I'm a little confused why they shifted up by 1 here. That seems surprising to me. But let's look at the bit patterns here. So F is 1 1 1 1, right? 7 is 0 1 1 1. Let's do these 4 at a time. F is 1 1 1 1. 7 is 0 1 1 1. 5, that is 0 1 0 1, 0 1 0 1, 1 1 1 1, and then 4 is 0 1 0 0. Okay. So they're going to grab 2 bits out of this somewhere using these to form a number. Now, if v1 and v2 are both 0, then it'll grab this. So here, let's start labeling like this. So here's what you get if you calculate it as 0. Now, if V1 was a 1 and V2 was a 0, you wouldn't get a 1 because they're shifting it. You would get a 2. So you'd get this, right? Let me maybe build the, underneath all of that, let me build the input table. So here we have N, here we have V1, here we have V2. Okay, so if the first variable is a 1, we get this guy. Now what if this is a 1 and this is a 0? Then V1, this is a 0. 1 shifted up by 3 is 2, 4, 8. Is that right? 1 shifted up by 3. It's 2 to 3, yeah. So it would be here, which is different from the other. So it's not commutative, is that right? Or am I misunderstanding something? Oh. 2, 4, oh, that's position number 6. I need to go like that. Okay, so that's better. So if one of them is a 1, and this is an implementation of AND, operator AND. Interesting. Okay. So if one of them is a 1, you get back a 1. That makes it sound like 1 means false. And that corroborates the other thing, which is if you pass a Boolean into the constructor, it actually inverts it when it saves it. So they're making 1 false. 0 and 0 comes out as 0, so that might be true. This is a false. This is a false. What happens if they are both 1? Then we get 8 plus 2 is 10, which is this guy here. And look at that. That is also coming out as a 1. If we get that this is a 2, then it's shifted up by 1, so we get not 3, 4. Wait, 2, not 3, 4, right? So if that's a 2, so it's a 2 and a 0, right? 2 in V1, 0 in V2, and we get a 1, 1. If it's a 3, so if it's a 1, 1, then we get 6 here, and it's a 1, 1. So we get back a 3. 1, 1 means 3. I'm noticing there are no 1 zeros anywhere. So 2 might not be, 2 and 3 might both mean the same thing. I think we're talking about a Boolean with 3 possible states. True, false, and unassigned. And I think the high bit must be the bit that says that you're unassigned. So it does not matter what the low bit is when the high bit is a 1. So 2 and 3 are both unassigned, but 0 and 0 are both true. And since this is an AND, when you AND true with unassigned, you get undetermined, right? You get unfixed because the true doesn't let you conclude anything because you need 2 trues to know what the result is, or to know that the result is true. But you can't conclude that it's false because that fixed thing could still come out true and make the whole thing true. So you have an undetermined result. It's either true or false yet until we know the other undetermined thing, right? So I think I get what this is doing. It's doing and or the way I would expect for this type if the low bit is an inverse of the state. So zeros mean true and ones mean false. And the high bit, the 2-bit, is on when the variable is unassigned. And with that understanding, I now know what I need to know about the L bools. The AND seems to be doing what I would expect, and they're implementing it through this lookup table. Okay. I think we're good to go. Let's keep reading. There we actually see a float for the first time. In the actual running code. Or probably a double, but whatever. I thought it said end clauses was 0. Oh, num clauses is 160. Got it. Okay. That's the input clause count. Got it. We got it. 53. Max learns. Yep, value of 2 because it's undefined. The verbosity. This looks like it's about to do something interesting. Luby restart. Luby. I wonder what that means. Restart inc. Current restarts. Otherwise, rest base. This is some kind of heuristic now or something. Find the finite subsequence that contains index x and the size of that subsequence. Find the finite subsequence that contains index x. I do not know what you're talking about. Size, sequence, size is less than x plus 1, sequence plus equals 1. Size is 1, x is 0. So that terminated right away. And we got a sequence of 0. Size minus 1 does not equal x. No idea. No idea. Probably a heuristic. I might need to look up what the LUBY stuff means in more detail. Conflicts is less than conflict budget. Propagation budget. Propagations is less than propagation budget. Okay. Ah, I'm at the end of the solve already. Okay. I'm skipping over something important in there. Let's take a look again. Gotta do F11 a couple times to find our way into the solve function. Don't care about this. Rest-based. All right, what is search? Search. No conflicts. Params, search params. Makes an L bool. Okay. Search for a model. Search for a model, the specified number of conflicts. Search for a model. Note, use negative value for no conflicts. Indicate infinity. Search for a model. I don't know what any of I can't understand. If a partial assignment that is consistent with respect to the clause set is found. If all variables are decision variables, this means that the clause set is satisfiable. L false if the clause set is unsatisfiable. L undef if the bound of numbers of conflicts is reached. Okay. You know, I'm coming through this and I'm doing all right, but I'm feeling like I could use a screen break. It's been almost 3 hours. I could use a screen break and I could use lunch. So I'm thinking of taking 30 minutes, maybe come back, and pick up right here. But I keep thinking like, oh man, I was originally expecting to be done after 2 hours and come back later in the day. But it looks like I'm going to be able to keep going for about 3 more hours. But if I'm going to do that, I should take an intermission. So I think I've made some progress. I have no idea how much of this has been like the meat of the solver yet. I've seen how the propagate works, and there's a lot of interesting stuff there. I am now going to try to figure out what search does. So, so I made some good progress, but there's good more to do. But yeah, I should take some amount of intermission. So, thanks Babel, thanks Brett, thanks for hanging out. Um, I will be back for anyone who wants to continue this project. And if you can't make it back, if you guys get busy with other stuff, I hope you have a good weekend. And I'll see you all around.